Okay. Okay. So, hi, I'm Steven. I wrote a curry compiler. It was fueled mostly by bad puns. So the compiler is Rice, and the goal I had with this compiler is I wanted to make an optimizing curry compiler. And so I want to share a little bit of how I did that, and mostly, a lot of the hurdles I ran into along the way, because it turns out there's some weird stuff that happens when you try to optimize functional logic programs. First, Rice. Rice is an optimizing curry compiler. And so why do we want an optimizing curry compiler? Whoa, what is going on? Well, that's an issue. Let's see. What on earth happened there? That is entirely wrong. There we go. Okay, there we go. We have slides. Okay, so let's try that again. So in this talk, I want to talk about a little bit about what is curry. So I know a lot of you have probably heard of curry, but you may not really be familiar with it. I'm not gonna dive deep into the semantics or anything. Because I want some of you to like me after this talk. Then we're going to talk about how do I actually do an optimizing curry compiler? What do I do at compile time? What do I do at runtime? Because it turns out you actually have to have a runtime, which I was very disappointed to find out. And then why is it hard? And I think this is maybe a little non-obvious because we've been writing optimizing compilers for a very long time. We've been writing optimizing compilers for functional languages, and we've been writing optimizing compilers for logic languages. Surely we can just smash the two together and everything will work. And it turns out, kind of. And then the last thing I want to ask is, did it work? Did things actually get faster? So, so first, what is curry? And so I'm going to give a very, very high-level overview. So if you're not familiar with Haskell or Prolog or curry or any of this, I'm sorry, but I don't have time to go very deeply into what everything does. So curry is a functional logic language, and so it's trying to combine the best elements of functional programming and logic programming. Syntactically, it's very similar to Haskell. In fact, syntactically, it's almost identical to Haskell. And semantically, it feels similar to Haskell, but there are a couple of really major additions. And so the first kind of major addition is we have this choice operator. That's the question mark. And so A or B returns both answers A and B. This is standard logic programming is we have non-determinism. So this is hopefully not new to a lot of you. And then we also have the idea of a free variable, also really standard in logic programming. And so these two constructs are really important for us because they change how we have to do a lot of our programming. We can't do just standard rewriting like you would do in a lazy functional language like Haskell. And instead, what we actually have to do, the other thing we have, and this is not important for the semantics. This is usually translated into more well-understood semantics, but we have an idea of functional patterns. And so this is something that some people are surprised by, but instead of pattern matching and just having a constructor here that I can match on, I can actually have a function here. And so the idea here is if I have a list, then I can take the first thing in the list and append it with a single element list that has an x in it, then the last thing in that list must be the x. And so this isn't used for the semantics too much, but I did use it a lot in the compiler because it was very convenient. And then semantically, this is the big difference between this and something like Haskell, like a traditional functional language, is instead of using just rewriting, we actually want to use narrowing. And we have kind of a specific idea of narrowing of outermost needed narrowing. There's a whole bunch of literature on that. We are not going into that. But this is semantically kind of how we define curry programs. OK, so why do an optimizing compiler? The big reason is this hasn't really been done before. We have had optimizations. We have had a lot of look at how to optimize the runtime system of curry, different evaluation strategies, things like that. We haven't really had a whole bunch of look at a whole bunch of research on optimizing Curry itself or functional logic languages. There has been work on partial evaluation, and there's been a lot of really good work on that. And then the other reason is I got, while I was working through my graduate studies, I got a lot of talk about like, oh, Curry, yeah, that's kind of a neat toy, but it's like way too slow to use in practice. And I'm not going to debate whether or not that's true. I don't think it is. I thought, well, maybe a more practical solution is, well, let's just make it faster. So, and there has been some work on partial evaluation. There's been a lot of really good work on that. The issue I had with it is there are a lot of things partial evaluation doesn't cover. Like it's a good optimization, but it's not the only one. It's also not automatic in Curry. So you can do partial evaluation, but it does require help from the programmer. And I want a compiler that just takes the Curry program and spits out efficient code. So the goals for this compiler, I have a couple of really important goals that I'm going to try to maintain at all costs. So the major goal is I want to compile to a low-level language. And so this is a bit different than what's been done with most Curry compilers. Most of them have actually compiled to, like, the two kind of standard Curry compilers are PAX and Kix, Kix2, which compile into Prolog and Haskell respectively. I want to compile down to a lower-level language, so like C, and obsess over a lot of the details and see if I can make them as efficient as possible, or at least as efficient as I can get to. And then I also want my compiler to be easy to extend. Once I have the bare bones of the compiler working, once I have the optimizer working, creating new optimizations should not be a hard task. And then it should generate efficient code. We are not talking about the efficiency of the compiler itself, but the efficiency of the code that it spits out. And so those are two related, but like very different things. OK, so how does my compiler work? The basic idea of the compiler is Curry programs are not really amenable to translation into C. So if I have a function applied to a let expression, in Curry we have an idea of what this means, but what does this what could this possibly mean in C? And there isn't really a good translation of that. So instead, what I want to do is I want to transform this into something that looks more like something I could write in C. And so now this is a variable assignment and a function call. I know how to do both of those things in C. And so the strategy here is I'm going to take standard Curry programs, and I'm just going to apply a whole bunch of translations and get them into a form that looks a lot more like C. And then after that, there's a translation into a slightly lower level imperative intermediate language called iCurry. And then we finally translate into C. But the core of the compiler is this transformation from the Curry intermediate representation to itself. And in fact, and so this is the part I spent a lot of my time focusing on. This is the part where it should be easy to write these transformations. And so here's the idea I came up with, is a transformation is just a function that takes part of the syntax tree and gives us back another piece of a syntax tree. So in this case, my transformation here is let floating. So I called it float. It takes, in the intermediate representation, it's called com, but this is just a function application. It's applied to a let. So let a equal x. So let takes a list of bindings and an expression. And then I just translate that into let my list of bindings. And then I apply f to e. So it's exactly the same thing here. It's just in this intermediate representation syntax. So this idea is really useful, and it turns out this idea is pretty extensible too. If I want more information, so if I want to pass in an environment or anything else, I just pass that into the function. I just add another parameter to the function. So this turns out to be a really useful core of an idea. And in fact, this is so useful of an idea that it's been around for 30 years. So this is not a new idea I've come up with. What I found, though, is Curry is actually a pretty good implementation language for this. The advantage Curry gives us is I can just write these functions in Curry. There's not a lot of different syntax here. It's pretty similar, and I don't have to do anything special. I don't have to add like any monads or anything like that. I don't have to write any sort of like quasi-quoter or EDSL or anything like that. I can just use curry syntax, and this works pretty well. So this is actually a really useful idea because I can handle I can write my rules as like individual rules. So here I've written an individual rule, but I want to apply it everywhere on the syntax tree. And traditionally, there's two ways to do that. Either you can write this as an entire traversal of the syntax tree, but that means every new optimization has to traverse the entire syntax tree. Or you can have one giant monolithic traversal that does all of the optimizations for a single pass. Both of those are kind of common ways of implementing this, and they're both cumbersome, hard to get right. And so the advantage here is it allows us to break everything up, but then we can later recombine things. We can combine these transformations to do a single pass of the AST. And so the way this works is I have a simplify function. And so simplify takes an optimization and just applies it everywhere it possibly can on the AST. And the way this works is just using the functional logic idea of I'll just try applying this rewrite rule. If I get a value back, I'll use that. If I don't, I'll just move on. And so this turns out to actually be pretty easy to implement. It runs until the transformation can't be applied anymore. So this is basic fixed point iteration. I just keep applying it until nothing works anymore. It applies transformations bottom up. There's no real reason you have to choose bottom up or top down. I just found bottom up tend to run faster and produce better code. This wasn't really surprising to me. And then adding, we can just add more information to a transformation just by adding more parameters to my function. And in fact, if I want to return more information, I can do that too. Instead of just returning an expression, I can return like an expression and maybe what transformation was applied. And this turned out to be invaluable when I was debugging the compiler. And then finally, if I want to combine two transformations, I just combine the two functions. I say I do either transformation T1 or T2. If T1 applies, I do that. If it doesn't, I try T2, I do that. If neither of them apply, I just move on. And so this turns out to be really easily composable, which is a really nice property to have in a rewriting engine. The downsides to this is transformations have to be terminating. If you have a non-terminating transformation, it will, this system will do nothing to check for that, and it will just run. If you have non-confluent transformations, which is very common in a compiler, this system is not confluent. And normally that's OK. Normally we don't care about that, but that is something to be aware of. OK, so how is this useful for optimizations? Well, it turns out an optimization most of the time is just a transformation. Not all the time, but it turns like in almost every optimization I did, I could just write it as a transformation. So this is case canceling. This is maybe the most important transformation for functional programming, either this or inlining. The idea here is I have a case of a literal value. I'm going to call it L. And then I have a branch that has literal value of L. I execute expression E. Well, I should just get rid of this whole thing, and I should just execute expression E. Really dead simple optimization. It turns out this saves us more time than like anything else. So this is really important to have in there. And the implementation is as simple as you would hope. If I have a case of a literal L with a branch that matches that literal pattern L and an expression, I just replace it with the expression. So this is great. But you might be thinking here like, oh, well, I mean, you have to deal with all of this kind of boilerplate for the intermediate representation. And that's true. It turns out we can actually get rid of a lot of that with functional patterns. So another optimization I implemented was shortcut deforestation. And the idea here is if I ever have a combination of full-dar and then function build, and it turns out you can rewrite a lot of list processing functions in the standard prelude in this way, I can just rewrite this to G applied to F and Z. This turns out to be a really useful optimization. It turns things that build a list and then consume it into just a single recursive function. And the implementation of this is just about as easy. I make an apply function here that this is used frequently in the compiler. It's just a function call, a call to apply, which is this is just the partial application function. And then I have a function f. I have a function fold_r underscore and build underscore. And then I can just use the idea of functional patterns to say, oh, I'm having a fold_r applied to a build. And it'll say, oh, it has to actually match these syntactic applications. And so then I can just replace this with apply g to f and z. And so this turns out to be a very useful way to write these rules. And in fact, the compiler is filled with rules like this. And so it doesn't actually look too far off from things like the macro language we saw earlier today. It's not nearly as powerful as that language, but it's pretty good for being just implemented in Curry. OK, so what are the problems with this? And so one of the problems is, let's say I want to inline this call to double. And so I think it seems reasonable to say that any call to double should return an even number, right? And so I should get back the answer 0 or 2. This seems like a reasonable thing to do. If we just do naive inlining, what we do is we say, oh, double. Double does x plus x. So what I should do is I should have 0 plus 1 plus 0, or 0 or 1 plus 0 or 1. The problem with that is this actually gives me back 4 possible answers. This is a really well-known problem of call time versus runtime choice semantics. Real major problem in Curry. It's really important that when I call a function where the parameter is used more than once, I should not evaluate that parameter multiple times. And so the solution to this actually turns out to be really simple. I just create a variable, x equals 0 or 1, and then I can do x plus x. And this gives me the semantics I want. This means I only get back 0 or 1. The reason I bring this up is not because this is like some hard unsolvable problem. It turns out this one's really easy to solve. The point of this is there are a lot of things that sneak in here. So one really common optimization, especially in functional programming, is common subexpression elimination. I might have 2 expressions that are exactly the same, and I might be able to say, well, hey, I don't really need to evaluate those expressions multiple times. That's completely valid in Haskell. It's a great optimization. You should apply it almost everywhere you can. It's not valid in Curry. I cannot do this under normal circumstances. And so we have to be really careful about this. Is not only do we have to implement the optimizations, which usually turns out to be the easy part, we need to figure out, are these optimizations still valid? And that turns out to be a much harder task. Great. OK, so that's the compile time optimizations. The implementation of those are pretty easy, but a big part of here is I've optimized the Curry code. That's great. If my runtime system is slow, that doesn't really help me much. If I'm spending most of my time just dealing with common tasks in the runtime system, then it doesn't really matter how much faster I make my compiled code. I mean, it does matter, but not nearly as much as the runtime. So I want to make sure my runtime system isn't just wasting a bunch of time. So runtimes, every decision I made about the runtime, the goal was to make it the generated code as fast as possible. So the first thing is we're doing computations with graph reductions. This is this is a standard for evaluating functional logic programs. Instead of evaluating a tree, our expressions are all graphs, so there's sharing. This turns out to be pretty fast, but it also can be fairly complicated. I'm using backtracking to handle non-determinism here. There are other solutions. So pull tabbing and bubbling are both other solutions. There are serious questions about things like completeness with backtracking. That is a wonderful question. We are going to completely sidestep that. So this system is not operationally complete. There are answers that it may not find. And then I don't, one major thing is I don't want to represent a let or a case expression. We're making a compiler. If I represent let and case expressions, I'm really making a translator to a really fancy interpreter. So I don't want to represent these. Instead, these should translate directly to C code. This is good, but it also turns out to be a surprisingly big problem. OK, so let expressions should build nodes in the graph, so they should be assignment statements. Case expressions are what actually does the flow of control. And it turns out the best way to implement them, for me at least, was a while loop with a switch statement. And so we can see that here. My let n equal unit, I make unit, I store that in a node, and then my case expression gets translated to a wall with a jump where I check the tag. And then there's a lot more to this, but this is kind of the basic framework for this. OK, so two major problems. Backtracking is usually pretty fast, but there are some cases where it's slow. Big example of this, I have factorial of this very long computation, Ackermann function of 4(1), very long computation, or 2. So I compute Ackermann, I compute factorial of this giant number, I undo the steps of fact. These are all necessary. This step is not. I don't need to undo these steps for ACK. I'm never using it again. And this was an entirely deterministic computation. And then I compute factorial of 2. Undoing these steps is a huge thing, because it's going to be every single step I did in here. And so if you have something like this, this makes backtracking unfortunately slow here. It turns out there's actually a pretty easy solution here. If when I'm reducing a deterministic operation, if it only depends on deterministic operations, so formally, if everything in a case statement is deterministic, then I don't need to backtrack it. And so as long as I keep track of that, and I keep track of that as a flag in every node, then I don't need to worry about backtracking, or I don't need to backtrack these things. The other issue, and I'm going to very briefly gloss over this, this is a weird technical point. What happens if I have to backtrack to basically here? And so the problem here is what happens if y is a non-deterministic computation that fails. So the way packs and kicks get around this is they normalize these expressions. That means there's only one case per expression. And so I never have this problem of I have to backtrack to the middle of a function. My solution to it, so yeah, I might have to backtrack to here. Remember, these are C functions. I can't just jump into the middle of a function. So my solution to that is, well, I'll just compute this like normal. If I have to backtrack to here, I'll just make this second function. The size of these functions is bounded, and so it increases the runtime code, but it doesn't actually increase the speed. OK, so finally, did this work? And the short answer is actually, yeah, it worked pretty well. So I was roughly, when I was comparing to Kix2, which is kind of the current state of the art, I was usually 10 to 50 times faster than the fastest settings I could get on Kix2. Most of the time, MCC, which is an older Curry compiler, was actually reasonably comparable to me, which actually surprised me a bit. Optimized code usually ran 2 to 5 times faster. It usually used like a third to a half of the memory, which was really nice. And then we were slower than GHC, which is not surprising at all, but I was usually competitive with that, and I was really surprised with that. So overall, I'm really happy with these results. Going forward, there's still a lot to do. I want to make Rice compatible with the current version of Curry. I want to bootstrap Rice, because right now it's compiling with PAX. And I want to add an LLVM code generator, and I have several other ideas. My takeaway here, though, is Curry can be just as efficient as functional languages. I don't see any reason why it couldn't be. So I think that argument from the start that, oh, Curry just isn't as fast as Haskell, I don't think there's any reason this needs to be true. But the low-level details really matter here, and I think it's really important that we need to focus on. OK. So, oh, that slide went away. OK. Are there any questions?
Hi, very interesting talk, thank you. What steps have you taken to try to increase your confidence that your optimizations are correct?
Well, for several optimizations, I had to go through and prove them by hand. So build fold actually turned out to be mess. It turns out like proving, so several of these follow directly from the semantics of Curry. There's a really nice paper, Natural Semantics for Functional Logic Programs, that gives semantics for Curry, and a lot of optimizations follow exactly from that. Things like build fold deforestation, I actually used methods from, there was a paper on free theorems for Curry that had a lot of really interesting ideas, and I want to explore that space further. But yeah, a lot of these I've had to prove by hand. And then also just generating a lot of test cases to make sure they did what I thought. Yes.
Thanks for the talk. This is more of a philosophical question in some sense. I wanted to take issue with the very early thing you said, where you said that people don't use Curry, and the reason they give is because it's not fast enough.
Yes.
And you put a nice caveat there. I feel like this is a myth that's misled a lot of the history of programming languages.
I would agree with that.
Yeah. So, okay. So I want to say that the thing that I feel like is maybe more important is having a good implementation in the sense of it has a good set of libraries, it has good documentation, it's used for actual things that people care about, and that's not to say that you don't need an optimizing compiler, but that these other things should also maybe be up there on the list if you really care about getting.
I 100% agree with that. I think a good stable compiler is really important. I think good libraries are really important. We have a lot of people that are much smarter than me working on those.
So I have a question concerning the possible non-confluence of your simplification rules.
Yes.
So you bootstrap the compiler with also with the Curry compiler, which does backtracking. Therefore, I guess in your compilation phase, you always produce the same the same optimized program.
But
there are also Curry compilers which really implements a fair search for backtrack, a fair search. That means in different compiling runs, you can produce different programs.
That is an excellent question. Yeah, I knew we shouldn't have let you ask questions. Okay, so I actually do have an answer for that, though. So right now, my way of combining two transformations is I say, like, do one or the other, take whichever answer returns first. There is no reason I couldn't implement this using like set functions or find value or something like that. That would do like find the value for the first optimization. If it fails, find the value for the second optimization, and I could roll all that up into a single operation. So I'm thinking like question mark arrow might be a way to do that. There are absolute questions on whether or not that would increase the running speed of the compiler itself. But I think that might be a reasonable way if you like really needed to order the optimizations. And there are definitely cases where that's important. Most of the time, you do make a good point, though, if we have like non-deterministically generated code. I'd be interested to see if there are other compilers that have non-deterministically generated code. You might be able to argue that's a feature, just because you could say, like, stochastically, this might help with the problem of finding, like, local minimum. But yeah, that is absolutely something I've been thinking about.
Just as a follow-up remark, you might produce all possible programs.
I've thought about that too.
And then compare them, make benchmarks on them.
There is one small problem with that. One thing I didn't really focus on is I can actually produce the entire optimization derivation, which is really cool to just watch a program slowly like shrink over time. That's a lot of fun to just kind of sit there and watch. Some functions have a shockingly long optimization derivation. And so what that would mean is if I were to produce all programs over time, that would very possibly like exponentially balloon out. And so that doesn't seem feasible. unless I put like some serious restrictions on it. Okay, thank you guys for your time.